Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers in the world of program synthesis and symbolic AI. I'll be your host, Brian Landers, and this podcast is brought to you by AGI Research Lab and Ndea. On the podcast today, we have an amazing author of a paper called Relational Decomposition for Program Synthesis. This paper is special in a bunch of ways. Number one, this is my teammate from Ndea joining us, so that's pretty cool. And then also, this paper was co-authored with our previous podcast guest, Andrew Cropper, who we're going to hear more about on the podcast. But without further ado, will you please introduce yourself?
Hi, Brian. Yes, first of all, thanks for the invitation. So my name is Céline, so I'm a researcher at Ndea. So I did my PhD at Imperial College in London, and then I joined Andrew Cropper's group in Oxford, where I stayed 3 years.
Oh, okay. I'm going to hear way more about that. I want to hear how you got into it and working with Andrew. So that is just the tip of the iceberg, but I'm really excited to have you on the show. Your work is so wonderfully suited for it's going to seem obvious because we hired you to join the team at Ndea, but just fabulous work that you've done. You're Google Scholar. Everyone should go check it out. Lots of great program synthesis work, and I'm happy to feature one of your papers today. So welcome, and I'm just excited to have everyone meet you. I guess one thing I wanted to share was just, the kind of, entryway into the paper is this idea that instead of trying to kind of solve a problem by looking at the whole puzzle, you can break it down into smaller pieces. And that is kind of opens up this magical door to solving more things. Would you agree with that kind of statement of, the sort of spirit of the paper?
Yes, it's a great summary of the paper. The main idea is by changing the representation, we can make a problem easier to solve. So that's exactly that. So the idea is really simple, just changing the representation and using your representation where we decompose the data, the examples, can make the actual problem much easier to solve compared to if we try to solve it directly at once. So yeah, that's exactly a change of representation problem.
I love that. That is so cool. There's a quote in the paper that was, I think you were referencing Bundy in 2013. Finding the right representation is the key to successful reasoning. We contribute to this view by showing that simply looking at a problem differently can greatly improve learning performance. So that's a pretty powerful concept. So I'm excited to get into the paper. But before we do that, I mentioned your past work across program synthesis and some other topics. If you kind of yourself step back and look at your breadth of work to date, what do you think, is there a story that jumps out? What story does that tell?
So basically, I've been interested in ILP for a long time, for maybe 8 years now. So I started by working with Stephen Muggleton, so during my PhD, on a different form of ILP, which is called meta-interpretive learning. So the idea basically is to search for proof of the examples and to extract a program from the proof. However, this approach to inductive logic programming is quite tedious because it requires forming the proof, so it's not very efficient. So after that, I looked at approaches to make the ILP problem more efficient. So I joined Andrew Cropper's group, and we looked at reformulating the ILP problem as a constrained programming problem. And this brought a lot of new ideas to improve the scalability and the search efficiency, which was really nice. But that alone wasn't enough to tackle big problems. So then I looked at problem decomposition approaches. So how to decompose a problem to improve learning performance. So instead of trying to solve all of the problem directly at once, which can be intractable for most cases, we try to learn some small rules that generalize only part of the examples, and then we try to combine them, and this makes the overall problems easier to solve.
Very cool. Yeah, you're sort of on a mission to, figure out how much you can do with this particular type of AI. Was there some moment in your career where, you went deep with inductive logic programming, with ILP, which was the topic of the episode with Andrew Cropper. So folks should go check that out and get a nice overview of the whole space. But yeah, was there some single moment where you were like, this is it, and I'm going to, write a ton of papers on this and go study with, Andrew after studying with Stephen Muggleton. Like, tell me about that.
It was more progressive. The first moment I realized ILP had a lot of potential and I wanted to work on it was during my master degree. So I did my master at Imperial College. And Stephen Muggleton was actually one of my teachers. So he was teaching one of my modules, which was called logic-based learning. And this is how I discovered ILP. And this is the first moment I understood that that's a lot of potential. And it was a really cool topic because we can learn from little amount of data. We learn models which are interpretable, so we can understand the logical rules that we learn. It has a lot of advantages as well. So we can generalize because of the representation language. We can generalize way beyond the training data. So the first moment I really enjoyed ILP, and this is what motivated me to do a PhD on this topic. And then I kept learning more about it. I wanted to keep studying this topic because it's there is a lot to be done. It's a field where we can easily have a lot of new ideas because there's so much potential. And lately as well, it has been growing rapidly with the recent meta-level approaches and the idea of using, so for instance, constraint programming or solvers to tackle the ILP problem. It opened a lot of new ideas and a lot of potential. So it was really an exciting topic to work on, which is why I stayed in the field after that.
That is so cool. Thank you for sharing more about that progression. I have one more kind of background question for you, which is, how did you write so many darn papers? Like, I was looking at, your past work, and even in like 2003 and 2004, you published 5 papers each of those years. Like, that seems like an incredible amount of output. How do you do that?
I guess it was a good moment to join Andrew's group because it was just the very beginning of this new paradigm of the ILP with constraint programming, and the very beginning of the new ILP system Popper. So this new idea spawned a lot of new ideas. So it was an exciting time where we could leverage a lot of the recent tool in constraint programming and translate a lot of ideas in constraint programming to ILP. So the paper that you wrote basically opens a complete new set field. It was a very exciting time, and it still is. There's still a lot to be done and still a lot of potential for this field. Yeah, and also on a more practical topic, I had the full research position. So I had basically all of my time dedicated to research. So I could really focus 100% of my time on getting new results and writing papers. So this was really a fantastic time to make progress in research.
Yeah, it's incredible to see, how much you got done, and it's really neat. I guess there's a lesson there about, sometimes it's about timing and just sort of, when you make an entrance into a field or collaborators you work with can all of a sudden have all this energy to it. I don't know how you reliably create that, situation, but maybe it's that kind of thing of like, you make your own luck, like you put yourself in situations where that could occur. Any advice for people trying to find that groove?
So maybe trust the potential that you see. So if this is a topic that you enjoy and a topic you believe in, then you will get a lot of ideas and you will be very suited for this topic. So I don't know, trust your instincts.
I know it sounds like, it's like a motivational poster, but it works. Like you actually did follow your curiosity and find success sort of exploring that. So I think it's worth taking note of. So one idea, you've been watching the Abstract Synthesis podcast to date, and I've been, pestering you for feedback. And you had a really brilliant idea, which was it would be good to kind of break down some of the key terms in each episode before we dive, deep into the paper. So I want to try that out with you as the first guest, where we test your idea. So I guess the first question is just, let's recap, how do you see program synthesis? Can you break that down for folks who might be new to the topic?
Yeah, I think it's important so everyone is on the same page and we can clarify for the newcomers. So basically, program synthesis is the task of automatically generating computer programs from a specification. So the specification that we give is that the user gives is what the program that we're trying to learn should do. So the idea is basically instead of writing a program directly. The user provides some intent, so what the program should do, what the property it should have, and so on. And the program synthesis system, it searches for programs that satisfies this specification. So basically, that's the main idea, that instead of writing a program directly, we search for a program that satisfies the specification among a certain space of programs.
Well said. Yeah, very succinct. And something relevant to the paper we're going to talk about is this idea of deductive and inductive program synthesis. Can you break those two down for us?
Yes. So basically, there are different specifications that we can provide in program synthesis. So let's start maybe with deductive program synthesis. So we take a full specification as input. So basically, we precisely characterize the correct behavior of the program that we want to learn. So maybe to give an example, if we want to learn a function that returns a maximum of two numbers, we can state that the result must be greater or equal than both of the inputs and equal to one of them. So this is a specification that fully characterizes the program that we want to learn. And then the goal of the system is to derive a program that probably is correct with respect to this specification. So as a result, in deductive synthesis, we find a program that must be correct, but we need to have this formal specification that needs to be full. By contrast, in inductive program synthesis, which is what I'm studying and the topic of the paper we are discussing, the specification consists of an input-output example. So the system is given a finite set of examples, and we must infer a program that generalizes these examples. So the main difference is that the specification is incomplete. So if we have a set of examples, there might be many different programs that satisfies these examples. So for instance, we can give as examples a pair, so 1 becomes 2 and 2 becomes 4. Then we can infer a lot of programs for that. So for instance, the program is twice the input, or the input plus 2. So there might be like several programs that fits, that generalizes these examples. So this is one additional complexity of this specification.
Wonderful. That makes total sense. There's one more kind of piece of, what these programs are, which is this sort of functional versus like logic programs. Can you give us an example of that? And there's some, or I read a lot of in papers, including yours, about how logic programs kind of magically shrink down the sort of constraint space. But I'd just love to hear kind of concretely how that works.
This comes down to the representation language of the programs that we want to learn. So in functional programming, we want to describe how to compute the output from the input. So typically, we write a program which is a composition of several functions that transforms the entire input to produce some output. So we might need to write a long chain of this long composition of these functions. So which can be a problem because in program synthesis, the search space grows exponentially with the depth of the program we're searching for. So if we're searching for a large chain of function, then we have a large search space to search, which makes the overall problem more difficult. So maybe to give an example, so in the paper, we take the example of inserting a letter, so the letter A, for instance, at the position 3 in a list. So if we want to do that with a functional program, we must explicitly deconstruct the list using head and tail or some similar function, then insert the letter, and then reconstruct the remainder. And each of these deconstruction step requires some additional composition in the long chain of composition in our functional program. So if we wanted to add a letter at the position 5 or 7, then we would require additional element in our chain, in our composition, so which would make the overall program much harder to learn. By contrast, in logic programming, so it's a declarative paradigm, so we describe what should hold, not how to compute it. So exactly we describe which relationship should hold between the input and output elements. So maybe to take the example again of inserting some elements in a certain position in a list. In logic programming, we can say that the first elements in the output are equal to their corresponding elements in the input at the same position. We can say that the third element is a constant, so the letter A. And then we can say that the remaining output elements are equal to the input elements at the position I minus 1. So it's the position shifted by 1. So we can learn 3 different rules to express each of these cases. And each of these rules has a constant size, regardless of the insertion position. So regardless of where we want to insert the new letter, if it's position 3, 5, or 7. And because of that, these rules are shorter. And because they are shorter, they are much easier to learn than this functional programming for this particular case.
That is so cool. Thank you for the example. And I know that one was in the paper. Can I tell you a funny side thing? This is a bit of a side rant, but I use Notebook LM, Google Notebook LM, sometimes to help prepare for interviews on the podcast. And they have these funny like audio overviews where there's like a fake, male and female podcaster like giving a, fun recap of the paper. And the AI tried to do this example, and it said, put an A after the Lion, put an A after the L, and turn lion into lamb. So it just like, it hallucinated like what was going on in the example, which is just so funny because it's like it was trying to do like a simple human friendly kind of, explanation, and it just failed because of, just the limitations of LLMs. But it was like the hands, the multiple, too many fingers on a human hand kind of a thing,
Yeah, that's a great example of the benefit of using them for logical representation, of the advantage we can have.
Exactly. And also this jagged intelligence thing where it's just like, it's so obvious that was not spelling lamb. It was just Laion. But it sort of just leapt to this false conclusion that no human would ever do, One other term that we should probably just explain, and we can keep it brief because I think a lot of the paper exemplifies this, is just decomposition. Can you say briefly, like, what is decomposition?
Yes, sure. It's an important topic in the paper. So basically, it's the idea of dividing a problem into sub-problems. Each of them are easier to solve, and then we can combine the solution for each of the sub-problems to obtain the solution for the overall problem. So that's the main idea of decomposing a problem. And the goal is to make the initial problem easier to solve.
Makes sense. I just realized too, there's probably one other thing we should share, and people should go watch Andrew Cropper's episode. But for the folks who haven't caught up on that yet, what is inductive logic programming, or ILP?
Yes, sure. So I definitely encourage you to have a look at Andrew's podcast. But just as a reminder, so inductive logic programming, it's a form of machine learning. The goal is to learn programs from data. But the specificity of ILP compared to other forms of machine learning is the representations that we use. So we learn logic programs instead of statistical model or something else. So yeah, that's the main idea. We learn logical rules, so logic program, which are sets of logical rules from data. So we can say it's a form of inductive program synthesis because we have sets of examples as input, and we learn a program as a logic program from these examples.
Makes sense. All right. Very good. And again, just go check out that. We covered with Andrew ILP at 30. So, 30 years of inductive logic programming, the whole space and the reflections on it, strengths and weaknesses. So go check out that episode for a deeper dive there. But let's talk about today's paper. So, I guess just to frame it up and make it, sort of approachable for people, what was the primary problem you were seeking to tackle with this paper?
So the main problem is what we discussed just before. So functional program synthesis approaches, they need to learn this long chains, this long composition of function. And this is difficult because the longer the composition that we need to learn, the bigger the search space we have, and the more difficult it is to learn it because program synthesis, the search space grows exponentially with the size of the program that we want to learn. So if we need to learn these big programs, it becomes really difficult. And the main idea of this paper is to observe that these functions in these long sequences of functions, each of them, so they manipulate the entire input, but each of them does not really apply to the entire input. So the core idea we came up with is to instead of trying to learn a function that manipulates the whole input successively, to try to decompose the input example that we have into sets of input-output facts and try to learn relations between each of these input-output facts instead of trying to learn this big chain of functions, which is too difficult.
Yeah, absolutely. And you gave the example before of like the, adding a character to the position 2 or position 3 of a word like lion, Lion. So that's a sort of concrete example of what you did.
Yeah, maybe I can give other examples. Another example.
Sure.
We focused on the abstraction and reasoning corpus. So one of the tasks, for instance, that we show in the paper is to draw 2 lines, so one horizontal line and one vertical line. And with this decomposition idea, we can focus on each of these two tasks separately. So first draw this diagonal line, which I think was red or something. And then separately draw an horizontal line with whatever color we needed to draw it. So we can learn these two concepts separately, which is much easier compared to having to learn both of them at the same time.
Yes. What was the programming language that you gave code examples in the paper? It was like, Y coordinate, X coordinate, and then, color was red, for instance. That's the kind of fact about like each cell, like within this arc grid. What programming language was that?
So we learned Prolog programs, which is a logic programming language. The reason for that is that it's expressive enough for the problems that we look at. Also we use Popper, an inductive logic programming system, which learns Prolog programs. So basically the decomposition approach that we develop is system agnostic. So we could use different learning systems. We could use any other system that is able to learn logic programs. And we could learn ASP programs or something else. But the nice advantage of using Popper for these problems is that Popper also can benefit from this decomposition strategy. So basically, it learns logical rules independently. So each of these rules generalizes a subset of the examples of the initial facts that we generated. And then it combines them to find the subset of the rules that together generalizes all of the facts. So because it can really benefit basically from this decomposition strategy.
Yeah. One thing I really loved about the paper, by the way, was just you framed it. That was great, by the way. You've introduced a bunch of sort of characters in the story with Popper. ARC, by the way, is the benchmark created by our co-founder, Francois Cholet, that we work on internally at Ndea as well. So it's really cool that you did that, and we'll talk more about benchmarks and other data sets here. But yeah, one thing that was really cool was how you kind of framed, the key questions you were seeking to prove in the paper. And the first question was, can our decomposed representation outperform a standard state, functional representation? And the second question was, can a general purpose ILP system like Popper, for instance, with a decomposed representation outperform domain-specific approaches? So I guess let's start with that second one, because it jumped out at me, this sort of domain-specific approaches. What do most people try to do now when they're solving, things like, for instance, abstracted reasoning corpus, like ARC, ARC-AGI-1 or ARC-AGI-2? And how does your sort of approach, differ from that?
So when we look at the literature on symbolic approaches for ARC or for other domains, we saw that there were lots of handcrafted knowledge given to these systems. So, for instance, how to manipulate objects, how to count, or a lot of handcrafted knowledge actually built in. And what we wanted to evaluate is how off-the-shelf general purpose system without too much uncrafted knowledge. Of course, there's some bias because there always is a bias, but without too much uncrafted domain-specific knowledge can outperform the specific approaches. So basically, we try to give almost the same bias, the same knowledge for all of the domains that we evaluated our system on. So for ARC, for string transformation, for list manipulation tasks, to evaluate how well we could perform with little domain-specific knowledge.
This is really special. Like, I think this is something to, make sure people understand. I mean, you gave a reference to past, winner of the 2024 ARC prize competition. And also they got second place in 2025, the Architects. Shout out to the Architects. They're super fun. They've got t-shirts that say the Architects that have them like in as funny characters. So they're like, they're a great team. But yeah, they pre-trained their, ARC AGI solution on something like, 500,000 examples versus, what you did in this paper was zero pre-training and using only like 2 to 10 training examples provided for each task. So that is like the stark kind of contrast between, the sort of two approaches, the sort of domain specific one and this more general approach. Anything to share about kind of, that sort of insight and seeing how well this sort of, other solution can generalize?
Yes. So one of the reasons for this big discrepancy is the representation language that we use. So we use logic programs, which are generalized highly thanks to the use of variables, and also ILP system are able to generalize from few examples. And the second reason is that because we decompose training examples into individual cells, for instance, for our grids, we makes artificially a lot more training examples, which is why as well we can leverage all of this data that we have in a much nicer way, so we can learn more efficiently. Yeah, and just the sheer approach, like the actual approach that we use, does not require any pre-training because we do not have any model with billions of parameters. That's not what we're trying to learn. We're trying to learn programs which are quite compact with the logical representation that we have. This is why it requires far less examples to learn them.
Yeah. I mean, that's super impressive sort of findings that you formalize there. You use some other benchmarks in addition to ARC, like a specific subset of ARC is this kind of 1D ARC, and also more traditional kind of approaches that I saw when you kind of cited earlier program synthesis papers, like even back to the beginning of program synthesis that use, I guess, like string transformations and list functions. How did you select these ways to measure to see if this decomposed representation could outperform these other systems?
So we picked these two benchmarks because they are classical problems in program synthesis. So string transformation, as you say, is a very classic benchmark. So it's often used in program synthesis. So also expected as a benchmark. And also it's a real-world benchmark. It comes from Excel spreadsheets. So there's actually some interest. So the benchmark that we used is some list transformation problem. So reversing a list or some program synthesis tasks, which are also quite classical. So we picked them because, they're quite usual in program synthesis. But also they fit with our decomposition approach because they are, all of these tasks can be represented as lists. So they can be decomposed into the individual elements that compose the lists. So this is another reason why we pick them.
That makes sense. And tell us about 1D ARC, for folks that aren't familiar with that data set.
So 1D ARC is simply a one-dimensional version of ARC. So instead of having 2D grids, you have 1D grids. I think there are 18 tasks. And the concepts are very similar to ARC. So basically denoising the task. I think moving from one position, copying, recoloring. It's very basically the same concepts, just one-dimensional. So they should be simpler to solve.
That makes sense. You just reminded me too, one of the other things in these kind of domain-specific approaches is like basic things that you need for, say, like an ARC puzzle if you're in that domain. So like transformation, like reflection, symmetry, detecting objects like lines and, borders and things like that. You just cook that into the actual solution, which is a really different approach than what you were doing, with ILP. How do you, break down, something seems kind of, mysterious about ILP in that, like, it's not that. It's not coming up with hard constrained solutions and cooking that into a system to solve just these very, specific tasks. How does ILP look at, approaching something like an ARC or, another kind of challenge set? And how is it sort of different than this sort of domain specific thing? I know we already talked a little bit about it, but I think it's really a notable feature of ILP, and it's not obvious. It's not intuitive why it works so well. Can you share more about that?
Sure. So I believe ARC is fundamentally a relational problem. So we need to learn relations between different parts of the input and different parts of the output. And this is exactly what ILP is doing. It's looking at input and outputs and trying to find relations between the two. One thing that's important to clarify is that ILP can use background knowledge. So if we have some additional knowledge, so if we know a definition for recoloring, for denoising, for whatever background predicates we may have, we can add it to an ILP system. And we could add it to the approach that we did. And it might perform better if the concept is relevant and helpful. So we only gave some minimal background knowledge because we wanted to evaluate how well it performed without these handcrafted features. But ILP can take as input this additional information, which we can imagine we can, for instance, learn in a lifelong learning setting. So cross-mining tasks, we could discover some of these concepts and then add them progressively to the background knowledge. So yeah, these are actually usable by an ILP system. So it's not because it cannot, it's because we made a choice not to give it as input. So yeah, that's an exciting direction for future work, actually. Which additional information should we give it? How can we discover it automatically? Because from the results, it's clear that some concepts are missing. We only achieved around 20% on ARC training, V1. So it's clear some information is missing. But how to discover it automatically, how to improve on that is an exciting direction for future work.
This makes sense. Okay, so I wonder, this is a bit of a maybe not, your area of study, but do you have any thoughts on just, is ILP in this sort of way of looking at things through relationships and also this decomposition idea within the paper that we're talking about? How does that map to like human thinking? Do you think that humans kind of think more like that versus this sort of, domain specific set of rules or more formal kind of program synthesis type stuff that feels very, it doesn't contain the intuition or sort of big cognitive leaps that humans make when they're kind of solving problems. Do you have any thoughts yourself on just kind of the relation of all these things to human cognition?
So I'm definitely not an expert, so it's just my random thoughts. So I think definitely we have large set of core knowledge that we combine, a bit like ILP is doing. Basically, we have this background knowledge, which is a big library of concepts that we have learned for our life that we will combine to make new knowledge. Actually, also thinking that as humans, we do this problem decomposition approach because simply our cognitive load is too low to look at a big problem all at once. So if we have an image, we always focus on part of the image and analyze it bit by bit instead of trying to parse it entirely, just simply because we have limited cognitive load and memory. But yeah, that's just my thoughts. That's an expert on these topics.
Thank you for, indulging my cognitive science question. It's just kind of a fun thing. It was, I think when you said lifelong learning, it kind of was like, that seems more like how humans kind of deal with, this sort of, problem solving and building up sort of learnings over time and then reapplying that to the thing, not even in a specific domain, but across, any new domain you see. So it just kind of sparked that question for me. So thank you. So one other thing, in addition to Popper, you tried out a few other systems, within this decomposition approach. Should we mention any of those? I'm talking about like Arga, and there's one called like Hacker-like. I was just kind of a curious name, but do you think there's anything worth mentioning to people listening?
I can briefly introduce them. So Arga is basically an object-centric approach that is based also on constraint programming, but it represents images as objects instead of lower level facts as we did. So there is a big difference in representation. So it performed well on completely different tasks, performed well on object tasks basically. Then we tried meta bias, which is a system specifically designed for these strict transformation problems that we talked about. So, for instance, extracting the name and the first name and last name of a person given their email address. So it's specifically designed for that. So it has a large set of primitives in its background knowledge to copy a word, skip a word, etc. So to parse strings. So it performs poorly on every domain except strings, basically. Hacker-like is a system designed to reproduce human thinking. So it's not designed to perform well at program synthesis tasks. It's designed to reproduce human performance on program synthesis tasks, and specifically for the list function tasks that we talked about. So reversing a list, appending at the end of a list, concatenating twice a list, for instance, or these kind of problems. These systems are domain specific. So you can observe that each of them does not perform well outside of the domains that were specifically designed for, which was a big result. Yeah, and each of them has some set of domain specific language.
Totally makes sense. So those were the ones that you were kind of comparing to answer that big question of the paper. I think you already mentioned some, just in terms of how this ILP, decomposition system did. You said 22% on RKGI1, I think, versus like undecomposed variants that you tested 0% across like time budgets, right? How did the ILP and decomposition approach perform, in relation to ARGA, meta bias, these domain-specific approaches?
Yeah, so the main result was that we can outperform these approaches, even though they were specifically designed for some domains. We can outperform them on the domains they were specifically designed for because of the decomposition representation. Only ARGA outperformed the decomposition approach and won the ARC because it performs really well for these object-centric problems. But ARGA does not perform well outside of ARC and won the ARC. And yeah, the main result as well was that without the decomposition approach, we perform terribly bad because it's just too difficult to learn these big, long rules, which are long chains of reasoning, because it requires learning long logical rules, which is way too difficult. And it's much easier to break them down and to decompose the problem. So that's the main insight of this paper.
Do you think that, you mentioned this a couple of times, but these chains of reasoning, do you think that's sort of like a weakness of current AI systems? I mean, your approach just sort of sidesteps that entirely, but it seems like it could explain some of the kind of weaknesses of LLMs specifically.
Yes, I think it's definitely a problem across different fields because it requires search steps, which is very large. So this fundamental problem applies to systems across different fields. And even in our approach, we can see it because even if we decompose an example, sometimes to find a relation between input and output facts, we need to learn a big rule, which is a long chain of reasoning. So to find a good rule that would explain some of the output pixel, we need to find one of these big rules. And the system that we use, so Popper, can learn rules with maybe 7 or 8 variables, and it struggles to learn bigger rules. So it's only partially solves the problem. So it makes some improvements. We don't have to learn this big chain of reasoning that applies to the entire input. So it solves partially the problem. But in some cases, we still need to learn these big relations to explain some output facts from the input, in which case it's still difficult. So any improvement that we can make basically towards learning bigger chain of reasoning would directly translate to better results. So yeah, that's only an improvement. It doesn't completely solve the problem of learning long chain of reasoning.
That makes sense. Yeah, thank you for explaining that. One quote from the paper jumped out. I think it sort of relates a lot to program synthesis and this kind of large search space challenge that it faces. Quote being the Bloomer bound, 1987, explains why searching smaller spaces leads to better generalization. This result from this paper says that given 2 search spaces, searching the smaller one is more likely to produce higher accuracy, assuming that a good program is in both. Can you help us just explain what's going on there?
Yeah, sure. It's a great result. So basically, the idea is that when you search for a program that fits a small set of examples, you may overfit. That is, you might find a program that matches the training examples that you have perfectly, but it does not generalize this to unseen test examples. And so the larger the space of possible programs that you are searching over, the easier it is to find such a program that perfectly fits the training examples, but it may happen by chance. It's not an actual program that generalizes to unseen test data. And so this result, the Bloomer bound, it's a way to formalize this situation. So basically, this result states that given two search spaces, assuming that there exists a correct hypothesis in both search spaces, searching the smaller space will lead to fewer generalization error, so better generalization, than searching the larger one. It's because in the smaller space, there are fewer hypotheses that can accidentally fit the example that you have by chance. If a hypothesis from the smaller space fits the examples, we have stronger evidence that this hypothesis captures the true underlying concepts and will generalize better to unseen test examples. Yeah, and the mathematical argument is actually super short. So I encourage you to have a look if you are curious. It's actually very short proof.
That makes perfect sense. You just reminded me too, we should tell everyone there's a lot of code. Like more than half the paper is like code examples. So go check it out. Like you can dive into all this stuff and try it out and see the examples that sort of led to these insights. Great job just kind of sharing your work, within the paper. I haven't seen many papers put that much of the examples like in the paper itself, Any thoughts on doing that and sharing the paper in that way?
No, yeah, I'm very happy to make it open source because it's nice that people can actually use it and give feedback. So yeah, if you do use it, and please reach out if you have any question or have any feedback at all. That'd be nice.
That's amazing. Hope someone takes you up on that offer. That's super cool. I guess, one thing to kind of, before we wrap up is about limitations was a big part of the story of the paper. For instance, in the paper, you called out specific things like global counting, like tasks that need, counting or aggregation remain hard. What are these kind of limitations with the decomposition, ILP approach here? What does that tell us about like the remaining challenges and maybe even kind of why AI is falling short of this kind of reasoning?
It's a great question because there is lots that needs to be done and still a lot of potential in this area. So, one limitation is that we decomposed basically the input and output pairs into the different elements. And because of that, the system is biased toward looking at each individual elements and not looking at the whole image as a whole. So that's why it struggles to learn concepts such as counting or this concept that require looking at the entire image. Maybe we need different representation and to juggle between all of these different representation, find which one is more appropriate for which kind of problems. Many different ideas we can think of to overcome this issue. Another issue that we discussed previously is which concepts we should give to the system, and it's how to discover it automatically. That's a great problem, especially for R, for the abstraction and reasoning corpus, because we know it's based on core knowledge, but it's unclear which one are these and how to learn them. So it's an important topic for this work as well. Approaches. So there is no guarantee that this is the best decomposition approach. There are many other ways to decompose a problem along other dimensions. So how else can we do it, and how much can it improve the performance?
That is so cool. There's a lot of I'm hearing calls to action for researchers to jump in and participate in this work. Those are the kind of other areas to keep pulling on. And I think Andrew's working on that at his lab. And just shout out there, he mentioned that he is always looking for students to participate in the program. Do you have any words of advice for someone who's interested in potentially working with Andrew?
Oh, definitely reach out. I think it's a very exciting environment to learn in. We did a lot of super cool work, and I really enjoyed my time there. So, and there is still a lot of potential and so many exciting ideas to work on. So, if you are interested, please reach out to him.
Very cool. All right. I will put that link in the show notes so people can easily find it. One last question for you, Céline. You've gone deep into program synthesis and this kind of world of symbolic AI. It's really cool to see the breadth of your work across all your papers, and I hope to have you on, to talk about other papers later in the podcast, or just come on the show to chat about program synthesis in general. But for people, just getting into this space and maybe just hearing about it for the first time, why do you think program synthesis is cool, and why is it worth looking into?
So many reasons. First, because it touches so many interesting topics. So it's in the intersection of many different fields, which is what I enjoy. So more formal reasoning, so logical reasoning, but also machine learning. So there are different ways to approach this problem. There's so much potential, so it's vastly unexplored. So there's a lot that can be done. So it's very nice field. So you can have a lot of ideas and make have a lot of impacts as well, especially in ILP because it's largely unexplored. And not enough people are working on it. So it's really a nice niche if you want to make progress in this field. And also there are so many applications of it. So the impact, the practical impact of your work can be huge. So we mentioned string transformation, more spreadsheets, which is an industrial application of program synthesis. But also ILP has been widely used in biology, pharmacology. There are a lot of domains where we need to learn from small amount of data with a lot of relations between the data and to learn interpretable models. So this is a clear way where ILP can have a lot of impact.
Absolutely. And if that stuff interests you, you should definitely apply to Ndea. Even though we're, not actively hiring, we're always on the lookout for amazing talent, just like Céline. So Céline, it is such a joy working with you every day. I'm so grateful that you joined the team, and can't wait to see what we all get up to in the future, and we can share with everybody when we're ready to share. But thank you so much for taking this deep dive on your paper. It's amazing, and hope to have you on the podcast again soon.
Yeah, no, thank you. I really enjoyed the discussion.
And thanks to everybody also just for tuning in. I know this is a very specific podcast. We're really just getting started and open to feedback. So if you have any ideas about ways to make it more approachable or more interesting, whatever it is, critical feedback is welcome. Let us know, and hope to see you on the next episode of Abstract Synthesis.